Hello, today we're going to talk about Bronsted-Lowry acids and bases. Okay, so the Bronsted-Lowry definition of acids and bases came about because these two different scientists were working on this theory, and it's based on protons. Now, protons by themselves, if it's just a proton and there's no neutrons, no electrons, that makes it a hydrogen atom, one proton. And if there's no electrons there at all, that means it's a positively charged hydrogen ion. So when I say proton, it's the same thing as saying a hydrogen ion. And you need to know both terminology there, both ways to refer to it. And then when we're talking about acids, acids are proton donors. So that means in solution, whatever the acid is can release a hydrogen ion into the solution. So something like hydrochloric acid, which is a really common one, in water, it can break apart and let off a hydrogen ion and a chloride ion. But the hydrogen ion is the proton, and that is contributing to the fact that it is an acid. Now, Bronsted-Lowry bases are proton acceptors. So that means they can bind to hydrogen ions from the solution. Very frequently, you will see things with hydroxide ions as Bronsted-Lowry bases. So they will take up hydrogen ions from the solution and bind them up into water. But it doesn't have to be hydroxide. It could be a lot of other things. A really common one is if there's a lone pair, like ammonia. Ammonia has a lone pair on the nitrogen that can interact with the hydrogen to form a coordinate covalent bond and making that turn into NH4+. So both of those scenarios, you are taking the hydrogen ions from the solution and attaching them to something to remove them. So they are proton acceptors. Okay, so this gives rise to something called a conjugate pair. A conjugate pair has one hydrogen different between the acid and the base, with the acid having one more hydrogen than the base. And so you could be asked to identify a conjugate acid-base pair in a given reaction. So let's look at a couple examples of this. If I start with something like, well, let's use that hydrochloric acid example from before. Let's just say hydrochloric acid is dissociating. It's aqueous. It's dissociating into hydrogen ions and chloride ions. The hydrochloric acid is an acid. It's acting as an acid because it loses its hydrogen. What's left over is what we call the conjugate base. So when an acid loses its hydrogen, what's left is the conjugate base. So there's an example. If I have something like, let's do phosphoric acid, H3PO4. If it releases one hydrogen, you're left over with H2PO4 negative. Because you took away one of the hydrogens, the charge goes down one. This is the acid. And what's left over when it loses the one hydrogen is the conjugate base. Now, the reverse is also true. So if I have something like H2PO4, let me write this a little clearer. And it's attracting a hydrogen, it's binding to a hydrogen ion to form H3PO4. This is acting as our base because it gains a hydrogen, accepts a proton. What it forms is the conjugate acid. Okay. So bases, when they gain a hydrogen, are the conjugate acids. In our ammonia example, can react with a hydrogen to form NH4+. The NH3 is the base, the NH4+ is the conjugate acid. So when it asks you to write these conjugate pairs, you want to write both things, so like HCl and Cl-. And typically you want to label them as well, which one is the acid, which one is the base. So NH3 and NH4+ are conjugate pairs. And you just need to label which one's the base, which one's the acid. The acid will always have one more hydrogen than the base. Now, some substances are actually what we call amphiprotic. So I like to think, so amphi means both or like amphibian and can live in the water and the land, or ambidextrous is both hands. So just think both. And then protic refers to the proton. So it can both accept a proton and donate a proton. And the most important example of that is water. Water can act as an acid and release one of its hydrogens. So this would be the acid, this would be the conjugate base. But water can also bind up a hydrogen ion and form hydronium. So in this case, you'd have a base in the conjugate acid. I should label this. This is acid, conjugate base, base, conjugate acid. So water is amphiprotic because it can do both of those things. There are other examples, and you should be able to recognize them. I'm going to bring back H2PO4 that we were talking about. This, we already mentioned, could act as a base. It can attract a hydrogen and bind it up to form H3PO4, and this would be your acid. Or the H2PO4 could actually lose another hydrogen and become HPO4 2-. So in this case, it's acting as an acid because it loses a hydrogen, and this would be the conjugate base. So if you see it starting with a hydrogen and having a negative charge, it's very likely that it's one of those amphiprotic species. Now this is a great time to review your oxides. So you can have metal oxides and non-metal oxides. So metal oxides are typically bases. Because they can interact with acids to form hydroxide ions, and you're leaving back whatever the metal ion is. And you'd have to balance that appropriately based on what type of metal is involved. But metal oxides can react with acids, so they are bases. Non-metal oxides, on the other hand, so I'm going to use N, non-metal oxides in water, act as acids. So they can form a weak acid, whatever the non-metal happens to be. I'm just using this as an example. The ratios might be different. But whatever your non-metal is, it doesn't have to be nitrogen here, can react with the water to form a weak acid. Now, the really common one is carbon dioxide, as your non-metal oxide can react with water to form carbonic acid. And then whatever your weak acid is can actually split apart into a hydrogen and a conjugate base, like this. And so that hydrogen ion being released is why the non-metal oxide is acting as an acid. A unique one would be aluminum. Aluminum oxide can be amphiprotic. It can act as either an acid or a base. It can react with an acid to form just aluminum ions and water molecules. So in this case, it's binding up a hydrogen, so it's acting as a base. But the aluminum oxide could also react in the presence of water with a base. It's two hydroxides to form this aluminum hydroxide compound here. And so because it's removing hydroxides, it's actually acting as an acid, which is a little weird, a little bit strange how it reacts, but you should know that the aluminum oxide is in between. It can be an acid or a base. The metal oxides are bases, non-metal oxides are acids. Okay, so here's a good example with an organic acid. So it says, what is the conjugate acid of this compound here? If you see COO- attached to whatever else, that's a clue that this is a conjugate base, or this acting as a base. What happens is that it can react with a hydrogen to form a carboxylic acid group. So in this case, I've got C2H5COO-. It can react with a hydrogen ion to form the conjugate acid, which is C2H5COOH. And so that's propanoic acid. because there's 3 carbons there. And the structure of that carboxylic acid looks like this, with the hydrogen attached to that end oxygen. Sometimes you'll see people put the hydrogen in the front, but more frequently, because it is an organic one, you'll see the acidic hydrogen added to the end. And don't forget, anytime it asks for a conjugate acid, you are adding an additional hydrogen. Now for this example, we want to label the acids and bases in the following reaction. We need to track the hydrogens. So from this side to this side, the HSO4 loses its hydrogen. That means that it's acting as the acid, and the SO4 2 negative, which was left behind, is its conjugate base. So these two things are a conjugate pair. The HCO3, from left to right, is gaining a hydrogen. So because of that, it's acting as a base, and what forms when it gains the hydrogen is the acid. And so these two things are a conjugate pair as well. Now our last example here, we want to show HPO4 2- acting as an acid and a base. If it's acting as an acid, it's going to donate a hydrogen to the solution. So you're leaving a hydrogen out. Rewrite it nice, a little bit neater. And what's left behind is the phosphate ion PO4 3-. Let's see if I could write this a little neater. So this is acting as an acid, this is the conjugate base. Now I need to use the same compound and have it act as a base, which means it has to interact with a hydrogen, bind up a hydrogen, and so it will form H2PO4 negative. Now your charges should always be the same on both sides, so that's another place where you can look to double check yourself. So this is a 2- charge on the left, and +1 and 3- gives us a 2- charge on the right. So that works. And then for our other equation here, where it's acting as a base, I have a 1- charge overall and a 1- charge overall, so that works out. This is our acid. So it is amphiprotic because it can act as both an acid and a base. So this linking question is why has the definition of an acid evolved over time? So we use like the Bronsted-Lowry definition, but we also have Lewis definitions of acids and bases. And really just as we're getting more information and like new discoveries, new data to support the new definitions, but also like being applicable in different scenarios. The Bronsted-Lowry definition is applicable for most of the scenarios you're going to see in an entry-level chemistry class, but like a Lewis acid definition is going to be more helpful if you're doing a lot with complex ions. Just for example, so if you see a question like this pop up, you really want to talk about just having more data, newer advancements, new discoveries that adds to our body of knowledge. Okay, this linking question wants us to talk about the conjugate acids of the polyatomic anions listed in structure 2.1. So there's a handful of them shown in structure 2.1. They are hydroxide, nitrate, hydrogen carbonate, sulfate, and phosphate. And so these are all bases because they are negatively charged. They can attract a proton. So the conjugate acids of these things will have an additional hydrogen. So let's do that for all of them. Additional hydrogen would give us water for hydroxide. This would give us HNO3, which is nitric acid. HCO3, add an extra hydrogen, we get H2CO3. CO3 2-, I just want to add 1 hydrogen, and the charge goes up by 1. SO4 2-, I'm going to add 1 hydrogen, gives HSO4-. And then for PO4 3-, you're going to again add just 1 hydrogen, and you're left with a 2- charge. So conjugate acids have 1 more hydrogen, and the charge is 1 higher because it has that 1 additional hydrogen. And this links to the acidic and basic oxides, which we talked about. Metal oxides are basic, non-metal oxides are acidic, and aluminum oxide is amphiprotic because it can act as either an acid or a base. Okay, so this linking question we didn't really talk about when I reviewed the oxides, but let's talk about it now. These oxides of nitrogen and sulfur can cause acid rain. And so they're nonmetals, so they can act as acids in the presence of water. For nitrogen oxides, so like if we have NO2, it can react with water from the rain or in our atmosphere, and oxygen, which is in our atmosphere, to form nitric acid. And that is a strong acid, and that will definitely lower the pH of rainwater. And similarly, the sulfur oxides, so you can have 2 of the SO2s reacting with water and oxygen in the atmosphere to form sulfuric acid, like this. And so both of these, they're forming acids, and those acids could then dissociate and give off a proton and lower the pH, making it acidic for acid rain there. So yeah, make sure you know these non-metal oxides cause the rainwater to be more acidic.